In the next section, I want to show you some applications of suffix trees. I'll show you more applications in the section after this. So I split it up a bit. This one's showing the direct versions where we just use the suffix tree in isolation. I just want to show you how many things they make easy. Recall, we store a suffix tree like this, the notion, the standard way to store a compact trie. But for the algorithms, we'll think about them as this, where we have the full labels. And when it's convenient, I'll replace the indices and the leaves with the full string. To keep notation short, I'll sometimes write ti to mean the suffix starting at position I or at index I. Okay, so that keep that in mind if it occurs on the slides. And that always includes the dollar symbol. So we usually say T0N for the input, but now I'll usually have T0N with, so this is a round bracket and this square bracket, right? This position at index N includes the dollar symbol. Okay, very interactive. Let's see if we have time to do those. The first thing we'll do is try to find patterns with the suffix tree. And if you have this small example, maybe I'll go back in a second to show it bigger. What can you tell about occurrences of this pattern A and A? What does the tree tell you? And it's the same tree, so here it is in slightly bigger. Well, let's try to get to the 60 again. I don't think it's useful to rush that part. Now it jumped to 60. Perfect timing. So I'll leave it for you to check. There's a bunch of things I'll just want to show you on the example here. So let's do it here. So if you have this pattern ANA, anything in the trie should search from the root downwards. So we start at the root and we find A, N, A. So here we have the pattern red. So after traversing with A and A, we're stuck at this internal node. Fine. So what does that mean? It means there's a whole subtree, namely whatever comes below this node, where everything in that subtree, any leaf in that subtree, has a path from the root downwards that starts with A and A. Right? Otherwise, it wouldn't be in that subtree. And that means all the suffixes that have leaves in that subtree, they start with A and A. And if a suffix starts with A and A, that means that's an occurrence of A and A in the text. And specifically, the indices of these two leaves are exactly the positions where A and A occurs in the text. And if you check, there's A and A here, and there's an overlapping occurrence A and A here. And that works out to starting index 1 and 3. Remember, we start at 0. That's why you can conclude this by the fact that you didn't fall out of the tree. You could traverse with A and A down the tree, and nothing was ever blocked. You always could follow an edge. And the rest follows from studying the subtree that you find there. So let's do this a bit more systematically. If we look at our string matching problem from Unit 4 in the formal sense, we have a pattern and we ask whether it occurs in the text. And the pattern occurs in the text if and only if the pattern is a prefix of some suffix of t. And actually, we can make this stronger. The pattern occurs at a specific position if it's a prefix of the suffix starting at that position. And because the suffix tree at least implicitly stores all the suffixes of the text, we can make use of that correspondence. And that's what we've seen in the example already. Formulating that as a proper algorithm would give you something like this. We try to follow down from the root, following a path, reading the pattern. And then several things can happen. So we follow down until we can no longer do this. And we can no longer do this for one of three reasons. We either get stuck. So there's a place where we would like to continue reading the next character, but there's no edge that allows to do that. That would be the case if we search NN, for example. So we start reading, we find one N, but then here there's no edge for N. So we fall out of the tree, or we're stuck in that node. And that means the pattern NN does not occur in this text. And that's true. Banana band doesn't have double N. The other option is we reread and we run out of pattern. That's what happened in the example with Anna. So we went down here. And so the pattern was finished when we read, but we could have gone on in the tree. That's the case where we have occurrences, as I discussed in detail just before. And the third case is we run out of tree. So we keep reading the pattern and then we reach a leaf. That actually can't happen the way I draw the tree here, because the pattern shouldn't contain the end of string symbol. And before reaching a leaf, there will always be a dollar symbol. But remember that we actually store this tree as a compact trie. So you might actually have that case because you jumped over a dollar symbol. And in that case, you would have to do the comparison with the leaf, but you will always find that you're actually in one of the two other cases if you look closely. So what this means is if we're given the suffix tree of a text, we can find the occurrences of a pattern. So find whether it occurs or return no match in time linear in the pattern. And that depends not at all on the length of the text. The text could be the entire web or the entire Wikipedia. The search time only depends on the length of your search query. That's the big benefit here. Now there's one subtlety that I glossed over so far. We don't usually want in string matching just to know, yes, there is an occurrence. So you search Wikipedia for some article, suffix tree, and it says, yep, I know something about suffix tree. That's not what you want. You want to see the article, or you want to know where it occurs, the search string. And for that, there's something else that we do in our suffix trees. Namely, we assume that every internal node has a pointer to the leftmost leaf in its subtree. So in this case here, every internal node has a pointer that points to one of those leaves and allows you to jump to one leaf in constant time. That's just one more extra pointer. It increases the space by a constant factor, but it's still linear in the length of the text. And so when we come back to this case here, when we read A and A, there's a pointer that we can follow in constant time to find the first match or some match. We have to be careful if we put it. What does leftmost mean? I took it as meaning the leftmost in the drawing of the tree. You could also try to make it point to the one with the smallest index. But at least in constant time, you can find a match. And in more time, you can find all the matches. But that needs potentially as much time as there are matches. So okay, I shouldn't do this in. If you want to find a single match, you can do it in time length of the pattern by following this one dashed green pointer. And now in this example, it's a bit silly. It's just one hop down anyways, but it could have been a huge tree. You can find all of the occurrences by exhaustively exploring the entire subtree. That actually has time linear in the number of occurrences, so it's usually also not slow. And so we can solve our string matching problem now much faster than anything we've seen in Unit 4. The only thing is that we have to spend linear time pre-processing on the text before we can get started.